So some other transformations. If I multiply the function by some constant number, so basically we're getting every y value and multiplying it by the same amount. Another way of thinking about that, again, because it's the y value that's going to change, if I group it with the y over the constant is equal to some function of x. Now, if that constant is greater than 1, the curve will become steeper. Say the constant was 5. So instead of a y value of 2, it's now 10. Instead of a y value of 3, it's now 15. And so on. So it gets a steeper curve. If it's in between 0 and 1, then the curve becomes shallower. Yeah? So similar idea. Say the constant was, half. Original y value is 1, it becomes a half. Original y value 2 becomes 1. So the curve's getting pulled down, if you like. It's going to become a shallower curve. Yeah? Again, we don't worry about negatives because the negative means something else with this. The negative means reflecting one way or the other. So we're really just interested in the number to see if we're getting steeper or shallower. And obviously k equals 1, well, I've got the original curve anyway. Okay. So a way of thinking about it, it's the y values that are going to be affected. So it's like we get our curve and we stretch it vertically or we push it down depending on what the constant is. But it's a vertical stretch. What that means is the domain of the graph won't change. I'm still substituting in the same x values. But the range might. I mean, if the original range was all real y, it's still going to be all real y. But say the range was originally between 0 and 2, well, if I stretch it out, that range is going to change. It might now be between 0 and 10 or something like that. Whereas if that constant is times the x, so it's not the function that's times the constant, it's the x. So everywhere you see x, you're replacing with kx. Interestingly enough, the same thing happens. K is greater than 1, we get a steeper curve, and we get a shallower curve. Now, the reason it's the same is because look at the position of the k when I've grouped it. When I grouped it with the y, the k was on the bottom of the fraction. Whereas when I've grouped it with the x, it's on the top of the fraction, if you like. So we actually get the same effect. K is greater than 1, curve is steeper, and k is in between 0 and 1, the curve is shallower. Some people prefer to think of it as x over k rather than k times x. So that way it's sort of consistent with the y one. And if you do think of it that way, then obviously this will reverse. It'll be k is greater than 1 and it's shallower. I think it's more natural thinking of it like a constant times something. So bigger than 1, it's steeper. In between 0 and 1, it's shallower. And I don't have to worry, it's the same for y, it's the same with x. All I've got to remember is, well, it's actually y divided by k, whereas x times k in that. This is going to be a horizontal. So it's like you know one of those chest expanders that people use. Look at big guns. Okay, so you're pushing the graph in or you're pulling the graph out by a factor. It's the domain that will change then. Because if I'm pulling the graph horizontally or pushing it in, it's the domain that's going to be affected. The x-intercepts will change, things like that. The range won't change. It'll still stay between the same y values. All right, so that's stretching. The reciprocal graphs. If I want to find the reciprocal of a graph, any x-intercept on the original graph will become an asymptote. Because the x-intercept originally had a y value of 0. Turn it upside down, you're saying 1 divided by 0 doesn't exist. So you get an asymptote. The reverse is also true. If the original graph had an asymptote, then the new graph, it'll be an x-intercept. If the original graph has a y value that's greater than 1, if I'm turning it upside down, then the new graph will have a y value that's less than 1. So anywhere the original curve was above 1, it now will be below 1. The reverse will also be true. Anywhere the original graph was less than 1, the new graph will be above 1, greater than 1. All right, let's have a look at some examples to try and illustrate. So on one graph, just to illustrate the steepness and the shallowness, not a particularly difficult one, but there's y equals x, our basic one, 45 degrees. So a half x, every y value is halved. So the line comes down, we get a shallower line. Y equals 2x, we now get a steeper graph. Every y value has now doubled. But that idea applies to every graph. So I could do it with parabolas as well. Woo! There we go. Y equals x squared. So y equals a half x squared will get me a shallower parabola because every y value is halved. So this new parabola should come in under the graph. Whereas y equals 2x squared, every y value is being doubled on the red one. So this parabola, the whole parabola should end up going above. We get a steeper parabola. Still the same idea as a straight line. X squared plus y squared on 4 is equal to 1. What do we end up with? All right, what shape do I start with?
Circle.
Okay. So we start with a circle, x squared plus y squared equals 1. Now the x I'm doing nothing to. It's the y. So I'm grouping it with the y. So y squared on 4, I'm now thinking of as y over 2 all squared. So every y value is changing. So am I going to pull this graph out or push this graph in? And the answer to that question is, well, what would make it equal to 1? It's now y over 2. What makes it equal to 1? 2. So I'm going to pull it out. Bang. To 2. So the circle gets pulled out to 2. We're stretching it by a factor of 2. Right? Y over k. K is the factor that I'm stretching it by. Pulling it out to 2. We end up with nil is. So there we go, that does 2. Let's have a look at a reciprocal one. So the original graph is actually just y equals x squared. But I've got negative x squared. Well, that means I'm going to reflect. There it is. Hang on, I've got 2 minus x squared. I'm now going to shift it up 2. So now I've got the graph y equals 2 minus x squared. I'm now going to take the reciprocal of this graph. Okay, those x-intercepts at that x value, I'm now going to have asymptotes. So those x values would be square root of 2 and minus the square root of 2. Now the original graph doesn't have any asymptotes, so the reverse doesn't happen. 1 becomes a key point, because if you turn 1 upside down, you get... So that y value is not going to change. Now 2, there was an important point. Turn 2 upside down, I get half. So I know the y-intercept. Bingo. And what have I just done there? Okay, I'm saying the top of that rectangle I just drew in is where y equals 1. So whenever that curve is above that line, the new curve will be below that line. So it'll be in this green shaded area somewhere. However, on the left-hand side of this rectangle, the curve is below 1, which means my new graph will be above. Oh, sorry, I did the negatives first. So, there's negative 1. On the left-hand side of negative 1, we were sort of below negative 1. It goes above negative 1. Over here on the right-hand side of negative 1, we were below negative 1. So we went above negative 1. Okay, let's do the other bits. Okay. So let's have a keep with the negatives. Between the asymptote and negative 1, the curve is above. So the new curve will be below. Over here, same again. Above goes below. Up the top here, in between the asymptote and this line, the curve is below 1, so it will go above 1, and so on, and we'll get something that looks like that, our red graph. So it'll be y equals 1 on 2 minus x squared. Okay. I'll just get rid of that. There you go. I've now dotted the parabola in, because remember the original parabola isn't actually part of the graph. That was just my construction work there. So 1 is a very important point to locate, where the y value is 1. Because you know that's where it's going to change from going above to below and below to above. Okay. X plus 1 on x. Okay. I've got two basic curves, and I'm going to add them together. So I've got y equals x and the hyperbola as well. We physically add the y values together. Now you can do that by sliding a ruler along. You can do it by just getting your fingers and going, oh, all right, I'm going to add this much on, and so on. But again, there's going to be some important points. Points of intersection are an obvious one to pick, because I know the answer is going to be twice whatever that y value is, because I'm adding the y values together. 0 is a good one to pick, because you're adding 0. Now in this case, I've got a vertical asymptote with 1 on x. That's not going to change when I'm adding. Just because I'm adding x to it doesn't mean all of a sudden I can now magically substitute 0 in. So that vertical asymptote for this will stay. So all right, we're going to add the y values together. Key points. Vertical asymptote remains, x-intercepts, well, there are no other x-intercepts. Points of intersection, let's add those together. So there's my first 2 points. Doing that, I tend to grab the smaller one and add it to the bigger one. I think that's easier. So I might grab another point here, add it to the line, add it to the line. And then I start getting a feel for what this graph's doing, because I'm getting smaller and smaller numbers, and this line is going to end up becoming an asymptote, because I'm going to be adding smaller and smaller and smaller numbers as I go along. And I can pick as many points as I like until I get a feel for what the shape's doing. And I can see, okay, righto. Whoop. A little bit bumpy when I did dot to dot, but it's there. The red graph would be y equals x plus 1 on x. Whoop, there it is. And so in fact, we end up with, as I say, y equals x is an asymptote, and our x-axis has remained, y-axis has remained as an asymptote as well. By the way, can a curve cut an asymptote? Because you are correct. You can cut an asymptote. You can never cut a vertical asymptote, because that's a point of exclusion in the domain. When it comes to horizontal and oblique asymptotes, that basically is just telling you what happens out in infinity. Everywhere else, it really doesn't matter. And so if it needs to, and we'll get to this later when we do more and more curve sketching, it is possible to cut those horizontal, or what we call oblique, ones at an angle, asymptotes. Vertical ones, and that's the misconception people have. Because you can never cut a vertical one, people get in their heads that you could never cut an asymptote. But it's the vertical ones you can never cut.